Hey, all you haters, players, and everyone in between. Stoner Dave here. And I want to continue that little video I did a while back where I was talking about why do so many wannabe guitarists think they know so much about electronics. Now, in that video, I had talked about a video that Scott Grove had done. There's actually two videos that Scott Grove did. One where he discusses it and keeps pointing at his amplifiers and talking about this thing that he's trying to say that is definitely not true. And then there's another one where he shows the back of a I guess it's a speaker or a whatchamacallit, the control panels, a mixer board. God. So he's showing the back of a mixer board and explaining how in his previous video he was correct, because it's showing these things that this box can do, right? It's showing all the different configurations for its output and its load handling, right? So what I want to stick to, because there are so many different varieties, what I want to stick to, because I've got kind of a little bit of a model that I'd pulled out. It's an amplifier that gets 200 watts across 8 ohms or 400 watts across 4 ohms. Now these, of course, are speaking about the load, right? So they're saying you plug an 8 ohm load into this speaker and it pops out 200 watts. Now, according to Nihilist Lives Matter and Scott Grove, if you were to plug in that second speaker and get that double power, the reason why is because the load is cut in half, so the power doubles. And if you look at Ohm's law, right? If we look at Ohm's law and we consider that we've got, same voltage and current, and then we do that with the load, and that's our only load, right? Yeah, we do see a doubling of power. However, if you were to actually look at Ohm's law and the actual laws and the rules that go into that, you'd find that every source has its own internal impedance, which is included in Ohm's law. So that means that when you plug in that second load, right? You got that 8 ohm load and you plug in that second load into that second jack. The power isn't dropping down so that you can get the 100 watts across each speaker. Actually, what you've done is you've actually opened up a parallel network that goes to the load. So what happens is now, instead of your internal impedance being 8 ohms, you cut it down to 4. Because you've just put a part of that load in parallel with each other. So, let me go ahead and show you some of these numbers that I figured out for you, so you don't have to worry so much about trying to figure it out for yourself. Okay, folks, so now I was going to go through here and look at these different amplifiers, these different Marshall amps, because I'd found quite a few different schematics here, or I'm sorry, manuals, which show the rear panel and what kind of power and wattage we get from the different loads, right? This particular site, it seems to have all the different amps kind of printed on top of each other. There's like I don't know, it's really hard to read this, right? So I can't see what it's saying to hook up as the impedance here. The only thing I really can see is that output is 30 watts. And we got some blah, 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 blah here. But check out this output selector. matches the amplifier's output to the load impedance. So that's saying that the impedance of the load and the amplifier's output, need to match, right? And it says right here, with all valve amplifiers, it is imperative that the amp is connected to a load whilst in operation and that the impedance selected on the amp matches the total impedance of the speaker cabinet or cabinets being used. Example, if the amp is running into a single 16 ohm cab, the amp should accordingly be set to 16 ohms. If running two 16 ohm cabs, the amp should be set to 8 ohms. If running two 8 ohm cabs, the amp should be set to 4 ohms. Now, each of these settings isn't, it's a setting. You turn the selector to select this impedance, right? And there's a setup inside there that allows this to happen just by changing where the output feed goes through. What's the impedance on that output feed? That's all it does. It just changes that a little bit, right? So that we can keep our numbers working. So that's the reason for the impedance selecting switch on this particular set of amplifiers, so that you can match different loads. They understand, hey, and you can see here, look, see the way they're connected here? So you plug in one, and it's kind of like this kind of a setup, right? So whichever selector you go to will depend on what this is doing, right? Where this is going from. So where this is going from and to. So you can adjust this to go to different paths of this. And what it is, if you have one speaker, you got this line, right? So let's say you've got one 8 ohm speaker. You turn the selector to 8 ohms. You plug in your 8 ohm speaker, which works out to be this guy right here, right? So we'll cover up this part. Yeah, no, we'll call it load 2. It doesn't matter. We'll cover up this part just because it's easier to see the connections when I do that. So you can see that right there. This right here is essentially two kind of ideas of what a Thevenin equivalent looks like. I mean, technically, this right here is kind of more like a schematic what a schematic diagram would look like. Like if you were to look at the amplifier and check where that's going, you would see something that looks kind of like this on each of the corresponding outputs for that impedance selector. You'd see something that looks like this. They aren't just going through and have a knob that just randomly selects an impedance, or they say, oh, the impedance load is fine at this. We can just, it's valid for 4 to 16. That's not how it works. Now, there are amplifiers out there that will say, hey, we can take a minimum load of 4 ohms, but we can guarantee an output of this much at 16 ohms, right? And you'll see that it'll say PX at 4 ohms, PY at 16 ohms, and 4 ohm min load. You'll see something like that, right? You'll see that on some amplifiers, right? They'll tell you that you get this much power at 4 ohms, you get this much power at 16. Do not go below that 4 ohm load. The reason why is because this amp is tuned to the 4 ohms. When the amp's tuned to the 4 ohms and you plug in that 4 ohms, it's going to give you this maximum amount of power. As you drop, or as you add more resistance here, this becomes different and lower, right? But it's not like it comes half or quarter of the power, right? It becomes some number in between there. The reason why they're able to do that is because of the maximum power theorem. Now, the maximum power theorem says that they're going to get maximum power here, and if they go any lower than this, you know how power is, what is that? It's I squared times R. Also, it's I times V, and it's also V squared over R. So as you can see in this correlation right here, an increase in resistance corresponds to an increase in power. See, the way that works is when you have a fixed power source. And that's what's called a Norton equivalent. We're not too concerned about trying to work on the Norton equivalent, but it gives you the same answers. It's just the final circuit, the Norton equivalent circuit, looks a little bit different than this right here. And for this guy right here, it's kind of easy. It looks kind of like this. So a Norton equivalent circuit will look like this. And this is R N, and this is R L. And what you would find if you were to do any kind of analysis of this is that the maximum power happens when Rn equals RL. And you're like, well, what the hell? Now you're telling me that the Norton resistance is the big one. That's the one that I should be worried. And it's like, well, wait a minute. Because there's another thing that happens when you do this Norton equivalent. You find out Rn equals RTH. That's right. The Norton equivalent gives you the same resistance, voltage, and everything. The only difference is the way that you draw out the circuit. And that's why I said it'd be a bit more complicated to try to draw this right here as a Norton equivalent, because I would have to first combine these resistances, and of course the resistors that we're dealing with were, what did we say, 4 or 8 ohms? I think they were 8 ohms. Doesn't really matter. The overall the equations work out to the same. Now in this situation, yeah, we plug in that second load. We do double our power, right? Because it cuts the resistance over here in half, and it cuts the resistance over here in half, which means our overall total resistance is cut in half, which means our current doubles, which means that since our voltage is the same, our power doubles. That makes sense. And it is completely valid for this setup. This setup right here, it is not perfectly valid. Here, if we cut our impedance, our power that gets reflected into the source, what is oftentimes referred to as reflective impedance, causes the source to dissipate more power than the load. This kind of reflected resistance or power back into the amplifier causes the amplifier to get extremely hot. The farther you are away from this in the negative direction, that is going to a smaller resistance, the faster it will burn up and destroy your amplifier, because more and more heat gets sent to the amplifier. Now, I know you think you know what the hell you're talking about, right? I know you think it, but right here, the Marshall amplifier, right in the owner's manual, is telling you that I'm right. This right here, it's telling you that I'm right. Let me see here. Let me see if I can find another one. Let's see. Not the same one. Go back one. Here we go. Now, forget which amplifier this is. It doesn't seem to... Oh. Is this the same book? I hope not. It is, yeah. So this is the 1959 SLP Marshall. And here you can see, we've got one speaker here, we got one speaker here. Connect speakers before use. Output 100 watts RMS. Warning. Somebody stamped a bunch of shit over the top of it, so you can't read it. Here's one saying that it's 50 watts. I guess they have a 50 watt and a 100 watt model. Okay, whatever. There's the effects loop, which we don't really need to worry about when we're talking about the output. This is the only thing that we're really worried about when we're looking at a Thevenin equivalent, was we're looking at what does this look like to the speaker, right? What's the load seeing? Because the load ain't seeing all of this stuff. The load ain't seeing all of this stuff, right? The load's only seeing this stuff. This is where it's connected at, right? It's got one that's in series, one that's in parallel. Or, sorry, wrong one. One in series, one in parallel. And let's see if we have something here. So what? 5 and 6. So 5 and 6 on the back. Loudspeaker outputs. These are for connection of an external load, i.e. speaker cabinet. See item 7. Item 7, output selector. Matches the amplifier's output to the load impedance. It's all valve amplifiers. Oh, see? So, yeah, there's different setups for different impedance so that you can safely go and stay at that 100 watts and safely use different impedances to match it, to make sure that you don't damage your amplifier. This is somebody who thought, hey, there are a lot of different speaker combinations out there, and I want to make it so that people can get the most performance out of whatever speaker they have. So they put an impedance selector on there. That's freaking genius, right? People say, oh, I hate Marshall amplifiers. Marshall's the worst. There's also a 50, I guess it's a 59XL. Let's see. Let's see. I don't know if this is going to give us the book. Yeah, we'll allow it. Look at that. Ooh, that's pretty. Look how pretty. Look at that, your inputs. So check it out. When they design these inputs, right? They want it to have high impedance, right? Because that preserves signal clarity. They also want it to match a typical guitar's output. Now, how do you figure out a typical guitar's output? So, I mean, we know that single coil pickups have output potentiometers that are half the value of the humbucking pickups. So that would lead you to believe that, you know, your typical guitar has a very wide range of output impedances, right? It does, right? So how do you rectify that? I mean, one way would be to make one input have one impedance, have the other impedance have the other input have another impedance, and to make people decide what kind of impedance they have and select which input they use. It's one possible way. But another way would be to try to average that out so that, you know, you can kind of get the typical guitar input. Because it is such high impedance, no matter what the guitar's output looks like, what's hitting this input is going to be very small, right? It's such high impedance, it's not going to allow a bunch of current to flow through it. It's gonna take that signal as best as it can. So you want, if you have a high output, you know, it'll have a little bit more when it's going through there. If you got a low output, it's gonna have a little bit less going through there. But at any point when it hits here, there's not gonna be any current going on. It's like a zero current interface. Such high impedance. And your guitar has high impedance, and all your pedals have high impedance. See if we can read this back. Okay, can't read that shit. What the fuck? There's some kind of a technical implementation. Ooh, here we go. Back page, back page. Oh, can we read it? Is there any way we can read that? I can't read that. But we can, oh, look at that. Okay, so output impedance selector matches the amplifier's output to the load speaker impedance. Your 1959 HW should be completely powered down before the output impedance selector is turned. As is the case with any Marshall all-valve amplifier, it is imperative that A, the amplifier is connected to a load whilst in operation, and B, the impedance selected on the amplifier matches the total impedance of the extension speaker cabinet or cabinets being used. One 16 ohm cabinet selector on 16 ohm, use either speaker output. Two 16 ohm cabinets, select an 8 ohm, use both outputs. 1 by 8 ohm cabinet, select an 8 ohm and use either output. 2 by 8 ohm cabinets, select a 4 ohm, use both outputs. 1 ohm cabinet, select on 4 ohm and use either output. Do not use any other combination of cabinets and or impedance. Doing so may result in damage to your amplifier. An extension speaker cabinet with an impedance of less than 4 ohms or 2 extension cabinets of 4 ohms or less should not be used with this amplifier. Failure to comply with any of the points raised in this section will result in damage to the amplifier. Now, all the rest of this shit I ain't gonna worry about. You know, selecting mains, all that shit, I don't give a shit. That's not the topic of our conversation. This is the topic of our conversation. The simple fact of the matter is that you cannot, under any situation, just go and cut your load in half and expect to get double the power. I understand there are amplifiers that will show you how you can cut the load and double the power. I've explained how that works right here. Right here, when I plug in this one speaker, we get whatever the power is from that voltage going across that level of resistance, right? That right there, half that power will go to this load. When we plug this in, we get double that much power going through the system. Half of it goes on this side, half of it goes to these two guys. Each one of these speakers still sees the same 100 watt load, but now because they're both connected to the same output, we say that it's delivering 200 watts. It makes sense. I mean, this isn't something I just made up and just thought I was going to go and try to pick on some old guy who you all seem to think knows every fucking thing about anything. No, I saw somebody who has a lot of people that follow him and a lot of people that use his advice, give him bad advice on what you can do with your guitar amplifier. These rules, they do apply to solid state as well. Check this out. Let me close this for a second and I'm just pulling up a schematic for a solid state amplifier. That's wrong. That's not the one. It's what is it? Oh yeah. There we go. And All right, so I'm just going to zoom in here to the output section. We don't care about anything else, right? So if you look at this, this is a solid state amplifier. Now, if you look, you see this line right here? This is a feedback line. This is not considered as part of the output because, as you see, if you follow this line down, it goes right back into the input. So it doesn't count as part of the output. So what you see here is that we've got 33 ohm resistors going across a 220 nanofarad capacitor that is feeding into an 8 ohm speaker. Now up here you can see that there's a 680 ohm resistor that's coming up here to the headphone jack. This right here, we don't have to concern ourselves with because this right here is only connected when the headphones are plugged in, which means that it's a different Thevenin equivalent that we'd have to deal with. But it does go to this capacitor right here. So being a parallel connection and this being such a high, it may bring down this resistance just a tad bit. Not enough to really be too much of a concern. But we'll notice that this speaker is an 8 ohm speaker. It's not a 16 ohm, it's not a 32 ohm, it's not a 4 ohm, it's an 8 ohm. Why? Because this right here acts as the majority of our output impedance. These operational amplifiers have very, very little output impedance, right? So things that we add like this right here to go to here, are there to ensure that when we do plug in this load, we're not going to have a lot of the power being reflected back into here and burning up here because this load is so heavy, right? And we don't want power losses to cause us to not get a satisfactory amount of power to our load. So we match the impedance, even with solid state amplifiers. This is, of course, the Marshall MG10 schematic. You can see here. That's probably easier for you to see. The Marshall MG10 schematic. And yeah, you can see that even though there's a lot more going on through all of this right here, something that we definitely know for sure, right? There is a Thevenin equivalent done here to determine this input impedance, right? Now, somebody had asked me, is Thevenin valid for non-linear components? And you can see that we have 2 diodes right here, which are non-linear components. It really does depend on how we have the diodes in there. Now, if these diodes were forward biased, we would have to do a lot of extra work to accommodate for what they're doing here, right? Because they'd be allowing all this current going in. But as you can see, they're reverse biased, which means that we can completely ignore them. They're blocking all the current there. That's the primary purpose of diodes, is to block the direction of current, make sure current only flows in one direction. So the Thevenin equivalent gets done here, and you can see here we have a gain stage, right? It's the input stage, and typically this is used as a filter to keep the signal going and give a unity gain, right? Now here you can see something that's kind of neat. You see that this splits over this way, and we have an overdrive stage. You can see clipping diodes right here. This is our feedback loop, which sets our amount of gain, and you can see there's a variable resistor right here set up in such a way to adjust the amount of gain of resistance between here, and we can, just depending on how this is set and the value of this resistance right here, kind of sets the amount of the gain that's going to be applied on this end here. And these right here are LEDs, which means that they're designed for soft clipping. All right. Essentially, this is the same as having an overdrive pedal. This is essentially an overdrive pedal, or a design for an overdrive pedal. There's lots of different designs for overdrive pedals. Let's not try to get involved in that. But here you can see there's volume controls. And this sets how much of this first signal goes through to the rest of the signal, right? So this is where we would look at what is our input, right? Our input, what we can adjust as far as volume, right? So let's assume this is at high point. So we have another output, right? Another source going to another input. Look at this. This is the tone controls. These are tone controls, right? What this is doing is adjusting our potential with this RC configuration, which is a very complicated little group of things, both in series and parallel. So we would have to Thevenize all of this right here, both from the point that's coming in and to the point that's going out. Because here we have another gain stage. And here we would have to do another Thevenin equivalent to make sure that we match this input impedance. And of course, this is a pretty high input impedance, and you can see there's 100 here with just a capacitor going down to ground. The reason why this capacitor is here is actually, it's kind of for tone, but it's more adjusting the impedance factor, going with this right here, kind of helping us to lower the impedance here to match the impedance here. Then we have this right here, which is another gain stage. Usually with this, we're trying to get what's called a unity gain, or we're trying to get more, get a little bit more gain, and we go that into another gain. It's called a filter, though. Usually filters are either unity gain or some kind of a boost, but it comes back down through all this wire right here to another resistor. And look, you have an MP3 input, okay? And you see these two resistors right here, right? And they don't matter. This right here doesn't really matter. This is an input for an MP3 player. So when the MP3 player gets plugged in, this comes into a source, and this impedance here is matched to get the most from here to deliver to here. And we take this and do our Thevenin equivalent here to determine what our input impedance has to be. And you can see here that this is right here, very high impedance, so not a lot going on here. This is this right here is part of the feedback loop, goes down over here. And this right here is, of course, another part of this, but you can see it's on the ground side. So it's really not doing much over here. It's just kind of raising the negative end of the speaker just a slight bit off of ground, that's all. But then we get here, our Thevenin equivalent matching the input impedance here. And here we have the feedback loop, and you can see it's kind of a more complicated feedback loop. And this determines what the overall gain of our power section is. And that goes out here, and you can see it's going to try to feed this speaker, which has a load which we have to match, which is why these resistors right here, this resistor and capacitor here, and this capacitor right here is used up. And if you don't know what this is called, this little section of circuit right here is what's called a Zobel network. And you'll often hear it described that it's there to help aid the speaker, right? What it's doing, this capacitor, is trying to put more capacitive reactance into the signal, because this speaker has inductive reactance in this signal. So this capacitor being down here is there to help get better power transfer because of the maximum power transfer theorem. Now, let me see here. As you can see, the maximum power transfer theorem, we have a source, an internal impedance, and a load impedance. As you can see here, this is a graph of the maximum power transfer theorem. This is showing the maximum power transfer theorem in action, where it goes the most. And here's some other bigger 3D things. And you can see here we got a little bit more. Different instances. See, inductor, capacitor, inductor. That's the way it works, right? That's the way it works. That's the Thevenin equivalent of this output circuit. Let me show you that again. This right here, this bottom one right here, this is the Thevenin equivalent of this circuit right here. So that people as dumb as nihilist lives can understand it. This is the Thevenin equivalent circuit to this output configuration. The way this is determined is, like I said, first we analyze this section to determine what it's doing, what it's feeding into this section. If this section is being used, because as we see, we have an option to either bypass this section and go through here, or use this section and bypass this one. You can even see it here when the switch is thrown here, which gets rid of this resistor, which is blocking that input. When that switch is thrown there, this switch right here is thrown, and you can see this switch cuts off the input from this line and brings it up to this one. It's the clean overdrive switch on your amplifier. It has two places that it operates at and one place where you switch it. That's called a dual pole single throw switch. Or is it single throw dual pole? Whatever, it's a single double or a double single. You see this right here? See this? It says jack in, and it's got this little broken line, little switch that goes to ground. What this is showing is that when you unplug the guitar, this cuts up, and all the signal will stop right here. It'll go to here and stop. It'll just go to ground. Nothing will go past it. That's kind of cool. That means that you don't have to worry about, like unplugging your guitar in the middle of a show to switch it or whatever, and worry about damaging your amplifier. Because when you unplug the amplifier, the signal stops here. Nothing is going to damage your amplifier, even if it's completely on. All right. So we do the Thevenins, Thevenize this, get what's happening here. Thevenize this to get what's happening here. Thevenize this to get what's happening here. Thevenize all this to find out what's happening here. And this is what we're talking about. The load, the output impedance. The load, the output impedance. Load, output, load, output, load, output, load, output. I'm going to keep saying this till I think that you may have caught a clue. So, when those are matched, we have perfection. If this drops lower than this, all that power gets reflected in here. Now, luckily, this is solid state, so really the power will just go across these resistors for the most part. Very little of it will actually end up going in here, right? Because when this goes down, this actually will act as part of the load. So it will still try to balance it out. So that's nice, right? That's a neat little trick for you. It'll try to balance it out so that you get your best performance, even if you have kind of a shitty match here. It'll burn up these resistors before it burns up this amplifier. unless you've got too big of a mismatch, in which case, yeah, the resistor's gonna push back onto the amplifier as well, which not good. All right, so hopefully that clears it up some. I've half an hour to go over this, but it paints a pretty clear picture. I mean, all of this right here, and look at this. This is the results from Google when you do maximum power transfer theorem. Look at how many pages there are. You think that's all of them, right? It's like there's only 10. Nope. There are 15 pages. I thought there was more than that. Yeah, 15 pages. This last page gets a little bit out into left field here, but go to page 9. Let's look at that. Oh, course hero. Let's see what it says. Let's see what Matt. So this is a DC network analysis. Yeah, we don't want to look at a DC network analysis. Come on. Ooh, Norton theorem and maximum power transfer. Look at that. See, it's not just Thevenin, Norton too. The thing is that when you do Norton, you end up getting the same results as you do with Thevenin. And Thevenin is much easier to demonstrate with multiple outputs, right? So you've got multiple output options. Thevenin is a great way to demonstrate how that works. All right. Is there anything I'm missing? I don't think so. I think combined with the talking and everything, I think that everything's been pretty well defined. I mean, I personally don't think that this video is completely necessary with how well I've described this theorem in the comments. I mean, I've actually posted, here we go, maximum power transfer theorem in AC circuits. This is what we're looking for. See? So should we read it? Do we really need to? Statement of maximum power transfer theorem in AC circuits. In AC circuits, the maximum power transfer theorem is stated as, in a linear network having energy sources and impedances, the maximum amount of power is transferred from source to load impedance if the load impedance is the complex conjugate of the total impedance of the network. This means that if the source impedance is R plus JX ohms, to have maximum power transfer, the load impedance must be R minus JX ohms. Yeah, that makes sense. And that explains why there's a capacitor in line with an inductor. Capacitors have negative J reactance. Inductors have positive J inductance. So yeah, if a source has an impedance with an inductor, the load will have to have an impedance with a capacitor, and vice versa. Past the ads. Explanation. For better understanding of the maximum power transfer theorem in AC circuits, let us consider a simple AC network as shown below. V, impedance from the source, impedance through the load, and we see there's some kind of a current. Looks very familiar. In this circuit, the source impedance ZS, the source impedance is ZS, whereas the load impedance is ZL. Let ZS equal R plus JX. Then for delivery of maximum power from the source to load, the value of load impedance should be conjugate of the source impedance. This essentially means that the value of ZL should be equal to R minus JX. This is maximum power transfer theorem for AC circuits. Note that in DC circuits, the load resistance should be equal to the source resistance. However, in AC circuit, load impedance is complex conjugate to source impedance. So that's the difference between AC and DC when we talk about this stuff. Now, I didn't want to go through all the complex impedance that could be in here, the calculating the J, right? Calculating the J, we have to have a frequency to calculate J. J changes. J is a small value typically. However, he can become large depending on capacitive and inductive amounts, right? How much capacitance is in your capacitor? How many what is it? Don't tell me. How much inductance does the inductor have? I was trying to remember that because it's always given an L. All right, so proof of the maximum power transfer theorem in AC circuits. In this selection, we will find the condition for delivery of maximum power from source to load in AC circuit, and then check if the condition so obtained is in agreement with the theorem or not. Let us consider the circuit shown above. Let us first find the current through the current through flowing in the load resistance. Let ZL equal RL plus JXL, and Z equal R plus JX. The value of current is given as below. Okay, and if you're not familiar with this, when you square the J factor, it becomes -1. So that's why they have the square root of the two things squared. Plus, that's actually how we add vectors. And if you weren't aware before now, you should understand that current is a vector. That's why it has the I value. And the J is another vector. And because of the way that we view vectors and we add and do all that fun shit with inductors, right? We can use Pythagoras theorem to add different reactances together and get their total. Okay, now let's see. Power to the load, I squared, blah, 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 blah. XL equals -X. Makes sense. Because of complex conjugates, see? And yeah, equal and opposite. And here we go. RL equals R. RL equals R. Sorry. RL equals R. All right. Do you need further proof? Really? Do you need further proof than all of this? I know I skipped a little bit with all of that, but do you really want me to read all of this to you? I mean, think about it. Look at that. X plus L. Baba-ding, baba-doo. Maximum power transfer theorem. We see that the load resistance should be equal to the source resistance network. The source network resistance. This is in agreement with the maximum power theorem, transfer theorem for DC circuit. Therefore, we can say that for maximum power transfer theorem from source to load impedance in an AC circuit, the necessary condition is that the value of load impedance should be equal to R minus JX, if the source impedance is R plus JX, since R minus JX is the complex conjugate of R plus JX. We can say that the value of load impedance must be complex conjugate of source network impedance, otherwise known as RTH. Thus, the maximum power transfer theorem in AC circuit is proved. The amount of maximum power transferred may be found by putting RL equals R and XL equals negative X. In information 1, the maximum amount of power delivered to the load from source is V squared over 4RL. Do you get that? Do you see that? The maximum amount of power delivered to the load from the source is the voltage squared divided by 4 times the resistance of the load. That voltage, they're talking about the voltage drop across the speakers, i.e., right? The voltage you would determine if you took the maximum amount of power delivered to the load and set that as the answer to this question, and then solved for V, right? So let's try that. Let me get a nice clean piece of paper here. So we're going to assume 100 watts, right? Equals max power, right? And that's because we're looking at a 100 watt amp. That's been said 100 times, right? You're saying that this is the amount of power that's delivered across the load. So let's see, 100 watts equals V squared over 4 times, and we said it's an 8 ohm load, I believe it said 8 ohm load. So times 8 ohm, 4 times 8 ohm. All right. So that's going to make that V squared equal to 32. I'm going to leave off the ohms because that makes it kind of clunky, right? I don't care about the what the units are. I'm only concerned about the numbers, right? 100 is equal to the voltage squared divided by 32. So that means that 3200, and I'm gonna go ahead and plug the units back in. Ohms times watts. What are the units on that? Oh yeah, volts squared. And we're trying to find out how many volts squared are in V squared. So that kind of makes sense, right? So what's the square root of 3200? Well, I know that 3200 equals 32 times 100. And 32 equal to 16 times 2. I know the square root of 100 is 10. I know the square root of 16 is 4. And I know the square root of 2 is square root of 2. So we have 40 times the square root of 2. And what's that equal? Well, I know square root of 2, but I don't quite have that down to be able to add it all in together that quickly off the top of my head. Times second square root of 2 equals 56.57 volts. Ooh. Now this voltage, of course, is the voltage drop across the load, across your speakers. This is what the voltage is looking like typically we use an RMS value, which means root mean squared, which I've gone over before. Check out my other video if you're too stupid to figure out what RMS means. It is not a radical music system or whatever the hell else you think it is based on your experiences with Scott Grove. Sorry, I hate to bust your bubble, but it's not. And we could actually go through, calculate what this power is, but, well, do you really need me to? I mean, this 1600, I mean, we already know it's going to work because we calculated this voltage off of this wattage, right? We calculated this voltage drop across this resistance based upon the watts going across this resistance. If we were to go through, right, use this right here. We know this voltage, the voltage drop across that resistance is equal to this, which means that the source has got to be pumping out double that because as the voltage drop, let me see here. As you can see, when we look at the Thevenin circuit, there's a voltage drop here and a voltage drop here. The voltage drop is how we determine the current. I know you people, you keep thinking that this doesn't exist, right? So when you look at it, nobody told you this existed, right? You've heard this talk about, oh, match the impedance, but you've never known what it meant. So you always just assumed this wasn't here. You thought that the 100 watts was all the power that's there, and that all of it was going across this load. Lo and behold, now you know. Half of the power that's coming out of here is going across here. It's dissipated across here. That's why you hear stuff like the maximum efficiency is 50% and nothing can do more than 50%. That was like a big thing in energy consumption for years. They thought that the maximum efficiency is 100%. Reality is if you make this load higher, more energy gets sent to this load, which means that the efficiency goes above 50%. You can do this almost to 99% efficiency by just going way higher than this load, right? The higher this load is above this load, the more efficient the amp is. However, the less power that gets generated. You end up not being able to, you don't get your power. You end up losing the power. Now, if you drop this load here, right, you make this load smaller, what happens, right? You got the same voltage, but the current's different now. Same voltage with different resistance. Same voltage with different resistance. This is lower, this is the same. If this is cut into half, right, now you have 1, 2, 3 halves of the resistance. You have 3 halves of the resistance. You don't have half the resistance because you didn't cut this resistance. You cut this resistance. You have 3 halves the resistance, or 1.5 the resistance. So what happens is these 2/3, right? These 2/3 get 2/3 of the power. This 1/3, he only gets 1/3 of the power. So while there is more power being generated, it's being wasted here in the amplifier. It's going off into heat, not sound. That's why you want maximum power transfer, so all the power that you're generating is coming out of sound. If you can't understand that basic concept, you're hopeless.